I'm very honored to have the chance to speak here. I joined the Northeast Regional Laboratory in 1990 after I obtained my PhD study in Glasgow. Stan was the technical director of the Regional Research Laboratory. I like the Regional Research Laboratory very much because you can do whatever you like. And I started my idea about the scale when I read Stan's book. When I arrived, Stan asked me to do something with error, raster error. I find Steve Carver and Chris Glaston, they are all doing the error. So I thought that we don't need so many errors. So I thought something else. Okay, I read this one, I find it very interesting. Okay, and read more, we find that scale is not only for geography and for cartography, for hydrology, for everything. Okay. And you can find recently we have more and more attention to the scale issues. A lot of books published as well. So I will try to extract some of the slides Stan have used in 1998, and then also show some of my work with Stan, and show like Daniel's work about the cartogram. This is the slides I extracted. It's a long slide, so a few slides by Stan. Okay. Stan said, scale actually is not a problem, it is an opportunity. Okay. And modifiable and unit problem is really for all the spatial data. You can ignore it, but there's a problem. Okay. And he used an example, okay, for the Leeds, Brantford region. Originally have 2,315 small units. If you want to aggregate the data into 33 wards, then if you use different criteria, then of course you have different results. Okay, and you can see the results do depend on the zone you use. Okay, and he said the previous work is wrong. Okay. Not wrong, but just a little bit of flow. You can. It is very dangerous to ignore this problem. And of course, she said that zoning system is a key part of GIS, and scale is a key unknown in the zone system. But, a big but. Okay, zone design is much neglected, and few zone engineer tools exist. Okay. And it's a hard problem because it involves the manipulation of both scale and aggregation. And there's little useful theory to guide the process. Okay. Spatial patterns are scale sensitive. Okay. But okay, how scale is handled at present, badly. Very badly is wrong. Very few studies, okay, use only one aggregation to one scale, and some assume that scale is known and fixed, but scale is not under user control. So scale and aggregation are inseparably interlinked. Okay, so spatial analysis and modeling assumes you know the scale at which pattern and the relations exist. Typically, you don't. Okay, so this is a problem. So it is important to start a design zone to manage the scale and the aggregation correctly. Okay, of course, for the aggregation, you have different optimization criteria, but this is not enough. If the scale, the aim is wrong, is not appropriate, okay, then what will happen? So we need to optimize, okay, instead of the aggregation itself, we need to optimize scale and aggregation together. So he suggested to change the scale and then produce one result, change it to another scale and another set of result. Okay, but how do you do that result? Because you have hundreds of maps, then he suggests we use animation. Okay, so this is visualization. Okay. So he said, You cannot optimize scale without first optimizing the aggregation, and you use the interactive process. We can do the optimization. Okay, this is the first part. I extracted a few slides from Stan's presentation. Now my work with Stan at Newcastle. It is about a map generalization. It is multi-scale representation of maps. Okay, to derive smaller scale maps from larger scale maps. Okay, what we have done is one natural principle for objective generalization. It was published in Cartography and GIS in 1993, and another algorithm for objective generalization of line features. Okay, and some people say this early open source algorithm we can find that. Okay. And the natural principle actually says, you see, if you are closer to an object, you see more detail. If you are far away from the object, you will see less detail. So in reality, we have the human eye resolution. Okay, so within this resolution, everything disappears. Everything disappears. So in this case, if you ignore all the spatial variation within the small unit, let's say this is the smallest visible size or smallest visible object, then we can achieve generalization. For example, this is the smallest size, and you can use a pixel and or a point to represent. Okay. For example, this is Hong Kong, map of Hong Kong, we can use a point, no problem. Okay. For example, you see this is a terrain surface, and if we project the small size down to the terrain surface, so you can know all the variations, you can generalize it. Okay, at a different level, we have different level of generalization. For example, this is a double river. If you put this into this as the smallest visible size, and automatically the river will be generalized from double to single at some stage. Okay. And then, okay, we can use any point to represent, okay, the smallest size. So can a raster or can a single point, and point at a different position, and in the end, you can generalize the lines very well. For example, this is a line, coastal line between Scotland and England. This is digitized from the map, ordnance survey map. This is the result by the algorithm. Okay. And contour lines, okay, 1 to 10,000, 50,000, 100,000, 200,000, 20 times reduction. You can see no problem, no intersection. Okay, no intersection. And if you use others, you can see this kind of result. Okay, I continued my work in this area, and then another part is that Daniel's work about the visualization. He produced the cartogram. Cartogram is used for when you present some result like U.S. election. This is one candidate, this another candidate. You cannot see really which one wins the election. But if you produce the cartogram, you see like this one, you can see this wins. Daniel's, he doesn't use the area itself. He uses symbol, regular symbol, a circle or a square to represent the area. So at the beginning there are some overlap, and then gradually you move the overlap, and then you try to keep the topology between the areas. This is why. So I forget about this. There are other kind of representation map alike. Another is the morphing. Morphing is very related. You can produce fairly good scale effect, continuous zoom in and zoom out. This is why. Another one is the linear map, like this kind of schematic map. And currently people use segment-based, like each segment you try to orientate it into horizontal, vertical, and diagonal. And we use the stroke-based. And you can produce multi-scale effect as well. So the multi-scale representation can be for DTM image and maps. And I forget about that. Just my last slide. Scale. Now you find that it's everywhere. People say God is everywhere in our life. So Because science, in science, skill is everywhere. So skill is the god of science.